Good, good afternoon, everyone. So today's meetup, we will mainly focus on DeepSeek R1 model. It's a model to use reinforcement learning to incentivize reasoning capabilities for large language models. And the R here stands for reasoning. So it's the first version of the reasoning model released by DeepSeek. First of all, I want just to highlight, maybe you have heard about this like throughout all the news, right? Blogs. So what is special about DeepSeek R1? First, I think it's strong reasoning capabilities because if the model, do not have a very good performance, all the rest is not, paid attention to or should be highlighted. So the first basics that a model that gets all the attention is because it does has strong reasoning capabilities. The second highlight is it is open source. So open source, it means it's like the model ways are open source. It's under MIT license, which means that you can use it for research, for commercial deployment. It's all free to use. And also, DeepSeek has released a very detailed tech reports. I think it's a very pleasant paper to read, comparing reading the previous OpenAI GPT-4 model, since it's a closed source model, so they didn't disclose much details in the technical report. Well, the DeepSeek, I think they write like a very good amount of technical details about the V3 model and the R1 model. And third highlight, it is cheap. So you may heard the rumors around of how they able to figure out a way to reduce the computational cost to actually train the model. And also at the inference, DeepSeek also provides a very cheap API call comparing to the closed source companies like OpenAI. So before the R1 is released, you see the available reasoning model on the market is OpenAI O1 model. So it is a multimodal model, which means that it can also reason on images. And you see the price, right? So it's like 1 million token for input is like $7.5 per 1 million token input token and $60 for 1 million per 1 million token for the output. So which is very pricey as API. Well, R1 is released and they provide much lower, cheaper cost of the API. So it's like 0.14 for oh no, it's like 0.55 for the not cached version and 0.14 for the cached core for per 1 million input tokens. And for the output token, it's only like 2.1, $2.2. So, and I also put here is like, does the model disclose chain of source tokens? So I will show example later. So it's kind of the secret source of the reasoning model to disclose how the model reason about the problem. So before R1 is released, OpenAI models has not disclosed any of the chain of source tokens until it is released because R1 kind of make it very transparent about the chain of source tokens along with the results. OpenAI recently also released the O3 mini model that they also disclose some of their chain of source tokens. And again, I will show you and then do some comparison later on. And in terms of the context lens, I see right now OpenAI still have a much larger context lens to provide comparing to DeepSeek model, both for the input context and the output tokens. Yeah, so that's the highlights about R1. And so here is an example when I try to call the R1 model and also OpenAI O3 mini model. I think you can just go to the DeepSeek or OpenAI or ChatGPT website and you should enable the reasoning mode there, and then you are calling the corresponding reasoning model. So I put a question as why 1 + 1 = 2. So that's a question I put there. And then you see the DeepSeek R1 model sort for 23 seconds and And the O3 model is much faster. It's like 2 seconds. And the DeepR1 chain of source token, so this gray area is chain of source token. So it's basically the internal thoughts of how our model is thinking about. And actually, it's very long and detailed. I'm not able to display all the details of chain of thoughts over here, and it's even longer than the results. Well, the O3 mini model is very short, so it's just like 5 lines. And recently, I read the news that O3 actually hasn't disclosed the full chain of thoughts tokens. They mainly disclose the summarized chain of thought tokens. So this output tokens from O3 model is basically just a summarized version of the full version of the chain of source tokens. And then you will see the rest. So it's the final result. Of course, it's like to me, it's like R1 seems to be very mathematical, while the O3 is more, like user. I think like put it in a easier way for the users to understand. I also checked the final. So both of the models give a summary output in the end. And actually, I like the summaries from the R1 model. It's like why this question fascinated people and what is the final answer out of that. Well, the O3 mini, it's just a very short summary of that. Like it's related to everyday experience. So yeah, so this is, I think you can all try and compare. And if you are really interested into chain of source tokens, I think the R1 is like the full disclosed transparent chain of source tokens that you can see in the output. Okay, so that's an example. And what excites people when DeepSeek R1 is out is because it's comparable performance to O1. So O1, so before R1 is out, I believe O1 is the most powerful reasoning model on the market, although it's a closed source. But I think it has very high reasoning capabilities across variety of benchmarks. Specifically, the benchmarks include math, coding, science, again, math, language understanding, and solving software issues. So I would say like if you look at the results published from the R1, so it's comparing to the December version of the O1, which is the latest version of the O1. It has comparable performance on coding, so it's like around 96. And this one is even slightly higher, I would say on par. And then but R1 is very strong in math. It seems R1's math capabilities is even stronger comparing to the O1 model. I also look at the O3 mini model. OpenAI released after R1 is released. It looks like the performance-wise, O3 mini model outperforms R1 in most of the benchmarks, like reasoning, coding, and also general task performance. Although not by a lot, I think in some of the language understanding, I think it still has better performance than R1. But I think the R1 still holds advantage in the mathematic problem. There it seems the DeepSeek is R1 is like a very strong math problem solver. There. Right now, like the R1 is still about like half the cost of the API call comparing to the O3 mini API call. So, how I want to structure today's meetup, I would go for the peeling the onion approach. So, if you look at the R1 paper, and then I figure out in order to understand R1, I need to understand R1-zero, which is the major contribution of R1. And then in order to understand R1-zero, I need to understand the GRPO is one of the policy optimization in the reinforcement learning proposed by DeepSeek. It's not proposed in the R1 paper, but it is proposed by a paper called DeepSeek Math. It's DeepSeek that proposed this approach to solve the math problem. And then in order to understand this, we need to understand PPO is another policy optimization. And in the end, it's one type of the actor-critic reinforcement learning approach. So in this meetup, I'm just going to like from from the center of the onion and then piece it up together from the reinforcement learning to PPO to the GRPO that is used to train R1, and then how we finally like piece it up together into the final R1 model as described in the paper. So first, let's look at the actor-critic reinforcement learning. Actor-critic reinforcement learning, so it mainly has two key components here. One is the actor. You can think of actor is also the policy model, so it's basically equivalent concept. You may hear both in the reinforcement learning framework. So the actor mainly learns and update the policies to generate which is the best action to take given the current state. So you can think about the actor model will takes the state as the input and it will output trying to optimize what is the best action to take given the state. And then there is a critic model. Critic model is a value model. So it's kind of like a feedback provider to evaluate how good the action taken. How good is that action? How is that related to all the expected rewards, future rewards? So it kind of provides the rewards for the actor model to improve so that it can take better and better action throughout the training process. So the first step is the policy is going to take a state and its output to action. And then the step two is the critic. So the critic will take in both the state and the actions output by the actor or the policy model. And then it will predict a scalar value to quantify the expected return or the cumulative future rewards. It is also called Q value. I think you may heard about Q value mentioned in the reinforcement learning. So you can think about the Q value as the expected return, or it's kind of reflecting all the cumulative future rewards you would receive for the future steps until the RL episodes ends. And then in the third, so basically once the action is performed, it will interact with the environment, and then the environment will output a new state, and also you will receive a reward, like actual reward. So the reward here is kind of like, okay, whether the math problem is solved correctly, or whether you win the chess game, right? So that is like a very straightforward, direct reward that you observe from the environment. And then the last two steps is like, given the observation, we need to update our actor model and the critic model. So in the actor model update, we usually in the RL, they want to update the policy in order to maximize the advantage estimate. So the key concept here is the advantage estimate. It basically is a function that helps evaluate how much better or worse an action is compared to the average behavior. So average behavior here is like regardless, or you just pick a random action at that state, and then you observe the Q value, for example, right? And then you just do an average of all the actions, all the possible actions you can take, and then take a kind of like a mean of that, and that is your average reward you would receive given that state. So basically, it's advantage estimate kind of tells you for each of the action how much better it is comparing to the average behavior. So this advantage is important because it will show up in the PPO and also the group policy optimization later. So one method, as I mentioned, is just to iterate through all the actions, and then we can calculate the mean of the Q values there as the average value. Another people usually do in the reinforcement learning is to calculate the temporal difference error. So the temporal difference error is basically there's two ways to calculate the reward. So basically it's like you can use the reward at time t. You can use the actual reward you observed from the environment plus all the future reward you would receive at the next step, right? So this is like the actual current reward observed plus all the future rewards. So this Q is like expected rewards of all the future actions. So here is like usually people also put the gamma over here as the discounting factors of the future reward. So this is your reward, total reward you would expect at time t. Another way you can calculate is just directly using the Q value to calculate the expected reward. So both of these two terms are related to the expected reward at current time t. So basically you calculate the deltas over there. So the deltas is kind of like your temporal difference as the vantage estimate over here. And people even like simplify it, like instead of using Q values, they directly ignore the action and they just focus on the value functions given the state. Forget about the action. They just because once you take action, your state will get updated, right? So this you just focus on the value of the state instead of Q values of both the state and action. So this is just like a modified and to me it's like a simplified version of how we just estimate all the expected reward based on the current state. In the final step of Actor-critic, so basically we need two updates. One is we need to update the actor model. The second is we need to update the critic model so that the critic can do a better job. So usually when people update the critic model, they trying to minimize this temporal difference error over here, so that the expected reward will get closer and closer to mimic the actual reward you receive from the environment. So usually for the critic update, people just take kind of a square error to minimize the square error of the temporal difference error over here. So I think that is the kind of the basic of Actor-critic. And actually, based on this, people has improved the policy update algorithm to make it more stable because in the original way of training, people observed that it's not stable and may not converge to the best action, and then people start making improvements over that. And PPO is proposed by OpenAI, and it provides a way to stably train the RL there. So let's see what is the major difference that the PPO has proposed. So in the PPO algorithm, there's still an actor and a critic. So remember the actor is just to predict which is the best action to take, and critic is to measure the expected reward or the future accumulated reward given the state. So the PPO here, it makes some differences in the objective function to update the actor or the policy model. So this is their objective factor, and we can break it down. So if like this RT over here, so this pi is kind of the probability of taking action A given a state T. So this is your new the new policy model or the new policy model that you want to reach, and this is the old one. Instead of just focus on pi, as you see in the previous RL update, they take a ratio of the new and the old one. So if this ratio is larger than 1, it means that the new policy will assign a higher probability to the good action. If the advantage is high, right? We want this ratio to be larger than 1. But if the advantage is low, meaning that the expected reward of that action is worse than the average, then that ratio will be smaller than 1. So the new policy will decrease the probability of that bad action. So this is like they put it as a ratio, and then they also apply a clip function so that it does not have like a big large policy updates and make the training more stable. And then let's look at the advantage estimation. So PPO also made improvement on how it is going to estimate the advantage. So this is the same formula as we see, like using the state and using the value of action to estimate the advantage estimation. And what PPO does is it adds an exponential smoothing factor, right? So it has a gamma, it has a lambda, and then there's an exponential term L over here from 0 to all the future stats. So the gamma here is a discounting factor. So it's as in any like normal IL, there's usually people put a discounting factor for the future rewards. And gamma is the smoothing parameter. It adds over there. And the eta is basically just a temporal difference. It's the same as in the original IL update. So when people set this lambda and gamma, they usually set it as like 0.95 as the default. But if you see your training is not unstable, you may want to decrease the lambda slightly, and also depending on whether your RL is focusing on longer term reward or shorter term reward, you can adjust the gamma like to make it lower so that you can more focus on the shorter horizon reward. So that's the PPO. And let's see, finally, we reach the RL that is used to train the R1. So it's called a Group Relative Policy Optimization. It's even a simplified version of PPO. So what is simplified is over here, the critic model is gone. So before this, we know like there's a critic model and there's an actor model. We need to update the parameters for both of these models. Well, in the group one, they only have the act model. So they only have the policy model there. And then for the advantage estimation, they use a group. So basically for one, the actor here basically is just LLM. So all the policy here, you can think about it as a LLM you want to train. And then they use the old actor model to generate variety of outputs. So they usually generate like 4 to 64 different outputs. I mean, that is the nature of the LM. Like every time you even query it with the same prompt, you will get a different output. So basically, they just take that and then take that variabilities of the outputs, and then they generate a group of outputs from the actor or the policy model. And then they directly calculate, okay, what is the reward for each of the actions? And then you kind of have like a group of rewards. And from the group of the rewards, you just do a very simple calculation comparing to mean, because the advantage function is just tells, okay, whether the reward is better than the average reward you would receive, right? Right now, the average reward is calculated by the mean of the group there. So it's like a simplified version of how you estimate your advantage function, which is a feedback to update your actor model. So that is a major simplified version here, because I guess you will see like why this DeepSeek R1 is trained with lower cost, and also I think this will plays a key part here, since it's only going to train like one actor model instead of two there. And yeah. So this is like from the paper of how they formulate the objective. And if you look at the objective, actually it's very simple to the PPO algorithm. The only difference is that right now you see the group, like this A estimate advantage estimation is from the reward divided by the mean of the group average of the reward, instead of a separate model to estimate it. So basically, it takes the mean of it loops through all the actions over here, right? So it's like I from 1 to G. So say you have how many outputs in your group. So it takes from 1 to G. And for some advantage estimation here, it will be larger than 0, right? So it means that that output is better than average output. And some of that will be smaller than the mean. And then this A will be smaller than 0. And over here is still a ratio. So it's still a ratio of the probabilities over here. So it's the same as the PPO over here. And this A is just by this simple calculates. And then they also do some divergence normalization to make sure that the new policy model does not deviate much from the old policy models. There. Yeah. So that's the main change of GRPO comparing to PPO. Uh, yeah. So that's pretty much all the prerequisites before I move to introduce the R1. I know it may take a while to fully understand, and I also recommend you to talk to DeepSeek or ChatGPT to understand it more because I think that's the best way to learn about like why they take this probability ratio, why they do the clip, and why this can work. Like without the critic model there, why just by a simple comparison to the mean reward of the group, it is already a good estimation of the advantage function. At R1-zero then. So look at R1-zero. So this is usually how LLM is normally trained, right? So it usually starts with the pre-training. It's kind of like the mass token or next token prediction, and it's fully unsupervised, means that you get a grab corpus of data, unlabeled data, and you just do the next token prediction. And it may not be good at following the instructions, but it kind of learn how the language is formed, understand the grammar, and kind of learning some about the language itself. So that's the pre-training. And then usually in the LLM, there's like a supervised fine-tuning. So this step is mainly to make sure that the LLM follow instructions. So you may get a supervised data set of the instruction and response. And then you fine-tune the LLM so that the model can learn, given the instruction, what is the response to provide. Uh, and then after the supervised fine tuning, you will do reinforcement learning to align the human preference, right? So you can do the famous one from the Instruct GPT by OpenAI about how we can align the model output with the human preference by training on a human preference labels. Given a pair of outputs, human provides, okay, which output is preferred by human, and then the reinforcement learning is going to use that pairwise comparison labels to update the model weights to align with the human preference. So in R1-zero, supervised fine-tuning is gone. Human feedback learning for the human preference-based learning is gone. All the R1-zero is just focused on the reasoning part. So the reasoning task here is the math, coding, science, where you kind of know the concrete answer. Like you like for example, whether the Python code work, right? You can just run it and then you know whether the Python codes give the exactly expected outputs you want. So basically it's like for all the reason tasks, you have a very concrete exact answer there. And DeepSeek R1-zero is mainly just to focus on those type of tasks. And it trains a reinforcement learning to basically train the LLM to reason about the problem and to reach the final accurate answer of this reasoning task. And the R1-zero, it starts with a V3 base model, and it's a 71 billion mixture of experts model with 37 billion parameters activated at inference time. So if you want to understand what is the mixture of expert model, we have also given a meetup on mixture of experts proposed by Mistral company. And then you can watch this to understand this new very popular architecture in LLM right now. So the key idea of the MOE is like you basically you are going to train a very large model, but at the inference time you are just only going to use part of the parameters, like a small portion of the parameters, so that you can reduce the cost of the inference, but at the same time leverage the capabilities of the really large model. So in the R1-zero, it runs purely depends on the reinforcement learning. So again, it's based on the group relative policy optimization, right? So in order to save the training cost of our RL, because in our previous RL um, prerequisite, in this RL, there's only actor policy model. There's no critic, right? The critic is estimated based on a group of outputs. So it's basically just update one model, so that will save the training cost to train now, and they also find it is also as efficient. And also it uses a very simple rule-based reward there. Because it's all reasoning-based tasks, so we kind of know the exact answer, unlike like language generation tasks, because there's no exact answer, right? But for the math problem, coding problem, you kind of know the exact answer, and you can tell whether that math answer or that coding block is correct or not. So basically, they use just straightforward accuracy reward, like just to evaluate whether the response is correct. It's like a very straightforward reward. And then they also put in some format reward. Format reward is just enforce the model to follow the certain output format of the model. So the prompt they claim in the paper is also very simple. So it's just like this is a conversation between user and assistant, and it asks the model to output all the outputs into this sync. So this is the chain of sorts tokens. And then after a series of chain of source tokens, there's these answer tokens, right? So the answer you can put like after the chain of source token, and then you can put your final answer over here. And then they can put the prompt about the specific task descriptions, right? So it can be a math problem or a coding problem, and then the system it will start generate all the outputs by using this sync and the answer there. And during the RL training, they also put a reward on the whether the assistant is able to, whether the LM is able to output the format in the desired brackets as instructed over here. So basically, it's I think the highlights of the R1 paper is actually the R1-zero. It's the R1-zero model because it shows another way to train the LLM, right? So you can just you just guide the LLM by a simple rewards of the whether the final answer is correct or not. You don't need to optimize the prompts for the LM, and then just train through a reinforcement learning framework, and then ask the LM to put out all the sync tokens, the chain of source tokens, and then when you run more iterations, there the LM is going to figure out the prompts itself, basically. So the prompt itself is the sync tokens, like how they create the chain of those tokens in order to maximize the reward in the end. And the aha moment that you may already see this image is like for example, the prompt over here, like the sync tokens over here, let's re-evaluate this step by step. It's just naturally happen. Like the LLM figure out in order to improve the accuracy of the math problem, I need to do a re-evaluation step. Yeah, so this is I think that's the power and beauty of the reinforcement learning of you just focus on the final reward and let the system figure out the path. Okay. So that's the R1-zero, and then let's see how they like train the final R1. Because the R1 model, as you see, like R1-zero model just focus on reasoning task, right? So they just focus on math coding, while the R1 is more a general reasoning model that should also handle the language understanding, human preference, all of that. So basically, they extend the capabilities of R1-zero to all the other general reasoning tasks as well. So in the DeepSeek R1, so this is overview. So I think it also echoes the previous questions on the supervised fine-tuning. They did do the supervised fine-tuning in the R1 model. So so R1-zero, no labels, right? So it's like Well, if you think about the reward is label, you can, but it at least doesn't require any human labels from that. So there are many four phases in the R1 training. Phase one is the cold start, right? So it starts with the pre-trained base model. Again, this base model does not require any labels. It's just next token prediction as any LLM trained on a large set of data. And then they use the DeepSeek R1-zero to generate all of those chain of thoughts tokens and the final answers.
Yeah.
And then they apply, in their paper, they mentioned that they use humans to do it. This is a very small set of data. And then they use humans to review those chain of thoughts and the final answers to make sure that it's correct. So they just warm up the base model through a small supervised fine tuning to get the base model to understand, okay, what is the format of what is the task about and what is the output format looks like. So this data, I think, is a very small data set that they cleaned up from the zero outputs so that you have some data about chain of the thoughts and the final answer from the model. At the phase two, they do the exact same reinforcement learning on the reasoning tasks, on the math tasks, on the coding and science problems, exactly the way they do the zero model. And then at phase three, they want to extend the model to more tasks. So basically, they extended not just on reasoning tasks, but also to other, supervised fine-tuning tasks like language understanding, story generation, translation, etc. So all those tasks in the supervised fine-tuning. And in the phase four, I think this phase three and phase four is kind of follows how people usually train a LLM. Like they do the supervised fine tuning first, and then they use a diversified reinforcement learning, including both the reasoning task and the human preference over there. So these are the four phases of how they train the R1 model there and the R1-zero model, I would say it is first, it shows how they want to do the reasoning RL to make sure the reasoning RL can work. It can also work to train R1 in the phase two, so that the reasoning capabilities will increase over time when you do this reasoning intensive task. And then R1 model also serve as a data generator for the model warm-up and the reasoning samples there. And they have detailed about how they call the zero model and either through human to clean up some of the outputs or through some general the model itself to put a general reward there to filter out the correct reasonings in the data. So in the phase one, it's just a supervised fine tuning, right? So this is just to use the R1-zero to connect a thousands, it's a very small data set, connect the thousands of chain of source data from the zero model. So basically you prompt it with a few examples and then ask the zero model to generate the outputs. And then you can refine the results through the post-processing by human annotators. Since it's just thousands of examples, you can hire human annotators to clean up to make sure that the warm-up data is of high quality, of chain of thoughts and results for that.
They're going to lose.
And then the second phase is the first reinforcement learning for reasoning. So it's exactly the same with the DeepSeek R1-zero. It focuses on reasoning tasks such as coding, math, science, logic reasonings. So all of these reasoning tasks are well-defined problems with exact clear solutions. So you know exactly whether that is right or not. And then the reward they use, so basically still a simple reward they use to see whether response is correct. And along with that, they put some format rewards to make sure that they put all the chain of source tokens in the sync brackets and the answer bracket for the final result. And then they also add, because they find something very interesting, because the model output may be in different languages just because the pre-trained data set may be in different languages, right? So in the output, you may see English, you may see Chinese, you may see German. Like it's a little bit confusing as a readable product output. So they also add a language consistency. For example, they see, okay, whether all the output is in Chinese or all the output is in English, right? So they want to make sure that the model just use one language as the final answer, or maybe using the same language as the question, as the prompt language there. So that's for the reasoning, like a very straightforward feedback. And then phase three is for both reasoning and non-reasoning data. So when the reasoning RL converges, so they use the checkpoint to connect the supervised data. The reasoning data coming from the IL model. So the reasoning data, they create like 600K model from the IL checkpoint. And then basically they create the prompts and then generate, because the IL model is able to generate the champ source tokens, right? So you will see the reasoning trajectories. And then the rejection sampling here means that basically the same query. And again, you left the IL checkpoint to generate multiple outputs. So some of the outputs is good, some of it is bad. And then they use the generative like a reward model. So basically they use for example, the model itself by just to check whether that reasoning and whether that prediction is likely correct or not. So based on the variety outputs of the model, given the one prompt, right? So the model is able to generate variety of outputs there, and then it uses basically another LLM, what the LLM itself, like DeepSeek V3 itself, the model they got at that time, they just to see, okay, whether that reasoning makes sense or whether that the final results is correct. And then they use the reward model just as a way to say, okay, which output is good to be included in the training data set, which output we should just ignore because the model believes that reasoning is wrong. So I believe this 600K will be of a little bit lower quality comparing to the human crafted thousands of examples in the beginning for the warm up. But I think it may already also serve the purpose, like based on the judge model. So all the qualities of this reason data is based on the judge model over here. And then and I think another here is like you need the reasoning prompts, basically the chain of source tokens in your supervised fine tuning. And before R1 is released, I believe that OpenAI has not disclosed any of their chain of source tokens in outputs. So they are they are opening it up right now for O3 mini just because R1 is disclosing them all. So OpenAI like O3 also starts releasing, but it's still a summarized version, right? So it's not a detailed version of the chain of source tokens. So I do not believe that the R1 is using OpenAI model to distill because actually they don't have any access to the reasoning tokens from the OpenAI model before. Like right now we have O3, but still the chain of source tokens is just a summarized, a very brief chain of source tokens. Yeah. And then there will be non-reasoning data as well. So it's just 200K. And for the non-reasoning data, so it's more like writing, Q&As, and it's not as straightforward as reasoning, but also have some general reasoning there. Because it's not like an exact answer, right? So you cannot say whether there are many different ways to translate. So you cannot just say that is the only right answers as in the math problem. So they just reuse the portion of the supervised fine-tuning data.
Yeah.
As the NAMA model, right? So you can get any supervised fine-tuning data for the non-reasoning data. And after supervised fine-tuning is done, then they train the model for all the scenarios, including both reasoning and human preferences. So again, in this reinforcement learning, so it's kind of like how people to align the model for human preference. So they use the rule-based rewards in the first IL to guide the learning process in the concrete, exact reasoning task. And then they also add rewards to capture human preferences, mainly for helpfulness and harmlessness. Helpfulness, they just focus on the final results. I don't think it mentioned that they just focus on the final summary, emphasizing the final response, correctness and relevance of the response to the user. While for the harmless, because they are going to disclose a full chain of source tokens for the response, so they also evaluate the chain of source tokens to make sure that that chain of source tokens are harmless in the output. Yeah, so that's the four phases of the R1 model. And this is basically in their paper of R1 comparing to Cloud GPT 4.0. And again, this in the paper, they still use the May version, not the December. Oh, this is about a 4.0 model. So it's like released in last May. And then the O1 model is released in December. So I would say, like, if you look at the English task, I think the O1 model still has an advantage there. Like, for example, for some of the Q&As, language understanding task is comparable, but I think the O1 model on English and language understanding Q&As, O1 model still has an advantage there. And for the coding, I would say is comparable on code for so this is a variety of the coding task. So I think it's well on the live code benchmark, the DeepSeek R1 kind of has some improvements. On code forces is comparable, while on also some other coding task, the like the last one, I actually don't know what this task is about. The last one, O1, seems like still has a huge advantage over R1 on this one. For the math, like DeepSeek is very, very strong in math, compared to all the other closed source model. And of course, like a Chinese language, I think DeepSeek R1 has the advantage on to understand the Chinese language. While the O1 model, I think it still has that advantage to understand the English language task. So I would say for math and coding, the R1 maybe has comparable or even better on the math. There as a reasoning model. And I believe like O3 has also improved their coding capabilities there, but it's hard to say. I think it's depending on user experience. Some users may also say that the Cloud 3.5 has the best user experience in assistance in coding. So I think it's maybe different people, different user experience may have a little bit different actual the judgment on the performance. Next is the paper also mentioned about distillation into smaller open source model from the R1 model, because the R1 model, over 600 billion, you may need a large memory to load the models in. They also mentioned about like how they also distill it into the Quen model and Llama model, like 8 billion or 70 billion here across the math problem, coding problem there. And in their paper, they mentioned that distillation into the smaller model from the big model leads to better reasoning than comparing to you directly run the reasoning reinforcement learning on the smaller model itself. So basically, it shows like using a supervised fine tuning on the outputs from the R1 model of this open source model is better than you just run the reinforcement learning on this smaller open source model. I think that's also interesting finding, like to show the power of distillation model can improve the reasoning of the smaller model. And also for the distill model, they mentioned that they only apply the supervised fine tuning from the 800K samples from the R1 model, and they haven't run any additional RL on top. And even though they believe that run additional, I think it will improve the performance if you run additional RL on the supervised fine-tuned model over there. And
Yeah.
in terms of the performance, they see the 70 billion llama model, like a smaller, well, it's still not that small, but comparing to the 600 billion smaller, like a 70 billion model, able to show comparable or better performance comparing to the O1 mini model. there. Although I do not think it makes sense to directly compare to 4.0 because 4.0 is not like an all series model, like fully focused on reasoning. Well, the 4.0 is more like a general type of models. Um, there, yeah. So this is what they talk about in the distillation is talking about like how they distill another smaller set of open source model from the R1 model itself. I think they release these smaller reasoning models based on these Quen and Llama versions. Yeah,
Yeah.
that's the end of the meetup, and you will find the recordings on my channel. So you will also find all the past series of LLM reading group meetups all there. And if you want to find out more about the mixture of experts, there's one meetup in the past just focusing on that. Yeah. And so all this today's meetup is about the whale and the onion. So just walk away with the onion and the whale. Yeah, that's it.
Awesome.
And yeah.
Okay.